Hi everyone. Now let's shift gears a bit and talk about object detection. But first, let's recap where we are. And so far, in our journey through computer vision, so we have been dealing mostly with image classification. So that means, given an image, the model tells us what category it belongs to as a whole. For instance, if we give the model an image, it might tell us this is a dog or this is a car. So you can see examples of this in this grid, no, shown here, where each image is labeled um, as either an airplane, a bird, a frog, a truck, and so on. So this kind of classification works well when the image has a single dominant object, and we only care about knowing what type of object is present. So it's simple and powerful, but also quite limited. So what's missing here? Well, imagine a more complex image, one that has multiple objects. Example here is a person riding a bicycle next to a dog and a car in the background. Image classification alone won't help us know where each of these objects is or how many are present. So that's where object detection comes in. Object detection does not only tells us what is in the image, but also where each object is located using bounding boxes. So as we move forward, we will build we will build on the foundation of classification and start exploring how models can detect and localize multiple objects in an image. Um, think of it as going from just naming the scene as a sample here. For example, this one is an airplane, and 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 of course um we will try to locate here what will be the where should be the airplane located here in the image. Okay, so think of it as going from just naming the scene to understanding what's happening in it in detail. Okay, so what is object detection? So now that we've seen what image classification does, so let's take a step further. So let's say we don't just want to know what's in the image as a whole, but we want to identify every objects individually within the image. In other words, instead of saying this, it is it is a scene. It is a street scene, or this is a photo of a room, for example here. So we want to ask, where is the dog? Where are the people? Is there a traffic light? How many objects are there? And what are they? So this is where object detection comes in. So as you can see in the image on the left, you see people, cars, signs, traffic light, even a dog. So so each object has a bounding box around the object. So and a label showing what it is. So on the right, we have a typical indoor scene. So the detector has labeled the laptop, bottle, wine glass, a handbag, chair, and many more. So the key difference from image classification is that object detection localizes objects and classifies them at the same time. So when object detection answers two key questions, so what is the image? Where is it located? So this kind of analysis is crucial for applications like autonomous vehicles, surveillance, smart retail, robotics, and more, and many more. No? And well, in the next slide, so we will dive into how these or object detection systems actually work and explore models like ULO and SSD that make this possible. So now that we've introduced what object detection is, let's talk about why it's why it is such a critical and challenging task in computer vision. So as we saw in the previous slides, object detection algorithms gives us the ability to not only identify objects in an image but also to localize them. That is to draw the bounding boxes around them and label what each object is. So this in this slide highlights two key components of object detection. The first is localization. So this means figuring out where in the image an object is located. It's not enough to say there's a dog in the picture. So we need to know exactly where is the dog is. So that is what the bounding boxes do. And object classification. So once we found a region of interest, so we will still have to determine what the object actually is. Is it a dog? Is it a car? Or a person? Combining both tasks makes object detection much more complex than simple image classification. So we are essentially doing two jobs at once. First, finding the objects and then labeling them correctly. So as you can see in the example image, the model has successfully located and identified several objects like people, cars, traffic light, a dog, and many more. So it is doing localization and classification together. So this combination makes object detection incredibly useful in real world applications like self-driving cars, security systems, or any environment where multiple dynamic objects need to be tracked and understood. Okay, next would be now that we understand what object detection does, so let's look at the actual models or object detectors that make it happen. So at a high level, object detectors are trained to identify what um, identify one or more object classes and drawing a bounding box around each object along with its class label. So like person, dog, or a car. So there are many types of object detectors. So some are traditional methods like this one, no? Hard cascade, classifiers, sliding window with hugs, or this one are, let me write this up. So the hugs are using histogram. So histogram of oriented regions, that is the hugs, or some call it hogs or hugs. So these are the traditional types of object detectors. That is not this type of traditional object detectors are not based on deep learning. Okay, these are the older methods were foundational but limited in accuracy and flexibility. So then we have deep learning models or deep learning based detectors, which are far more powerful and accurate. For example, here we have the RCNNs, the SSDs, or the we call it the single shot single shot detectors, and we have this YOLO. YOLO is let me write this is this tab, no? You only look once. Then we have the Retena net and efficient net. So these deep learning models are the current state of the art. So we also divide them into two major categories. So what we have here is um, the two-shot detectors. These models work in two stages. So first, they generate region proposals, basically suggesting where objects might be. So then they classify those regions. Examples include the RCNN here, or the faster RCNN. We will tackle this one later, no? And next is we have this single shot. So single shot detectors. So these models do everything in one go. So they simultaneously predict both the location and the class of objects in a single pass. So this makes them faster and more suitable for this one is suitable for real time applications. So these examples are the YOLO and the SSD for this one, on the single shot. So depending on your need, whether it's speed or accuracy, so there are different models available for different tasks. And we will be diving into some of these in our next sections. Okay? So let me remove this one. Oops. Lah, nagkarat akong screen to. All right. Okay. Formal Wikipedia definition. So, um, okay, to formally define what we have been talking about, so let's take a quick look at how Wikipedia describes object detection. So, object detection is considered a part of computer vision and image processing. Essentially, it's the technology used to detect instances of semantic objects, meaning objects that carry meaning, or belong to a certain class, like humans or people, buildings, cars, animals, within digital images or video streams. This definition might sound technical, but it summarizes the main goal. So where we are teaching machines to look at images and not just see pixels, but recognize things. So in Wikipedia, Wikipedia also mentions um, two common and well-researched applications. Example here is the face detection, which powers features like face unlock in phones or tagging in social media. We have this pedestrian detection, which is crucial in self-driving cars or traffic surveillance systems. And of course, we have object detection has a broad applications with regards to image retrieval. So like searching for objects in image databases. And we have video surveillance where identifying and tracking specific objects, like example here is people or vehicles. Okay, so this definition gives us a good academic grounding and reminds us just how practical and widespread is object detection is today, from everyday conveniences to critical safety systems. So object detection plays a major role. Okay, so next would be, okay, we have this object segmentation. So now let's talk about another concept that is closely related to object detection, but goes even deeper, the object segmentation. So while object detection helps us identify where an object is using bounding boxes, segmentation takes it to the next level. Instead of just drawing a box around an object, segmentation classifies every single pixel in the image. So that means we don't just know that a person is somewhere in the bounding box. So we know exactly which pixel belongs to that person. So example, the road here, the trees, the buildings, and so on. So this technique is called pixel level classification, and it's incredibly precise. So you can see that in the image here, so every part of the scene is color coded based on its class. Example here, people are one color, roads another color, and cars, and so on. So segmentation is crucial in applications like autonomous driving, where it's important to distinguish road from sidewalk in this case, or pedestrian. Medical imaging, where each pixel might represent different types of tissue or tumors. And also in augmented reality, where pixel accurate object masks are needed for overlays. While it while while it's more accurate, segmentation can also be more computationally expensive and relies on different algorithm or other algorithmic approaches. Like example here is we have the fully connected networks, UNet, or mass RCNN. So we have, let me write this up. So there are other models. Let me so like we have UNet. UNet is the another model for segmentation. and mask RC and N. So we will tackle these two models here. So in short, if object detection tells us what and where, segmentation tells us that, um, well, in object segmentation, it tells us what and where also, but it will tells us what be the exact shape and extent of that object. Okay, let me remove this one. Okay, so classification versus detection versus segmentation. Okay, so at this point, we have introduced three important concepts in computer vision: the classification, detection, and segmentation. This slide ties it all together by showing how they differ and how they build on one another. Okay, so first is classification. So at the most basic level, classification answers the question, what is in the image? So as you can see here, so it's just recognizing, let me use the pen. Okay, let me, oh, there's a problem with my mouse thing. Okay, okay, this one. So what we have here is we have classification. So at the most basic level, classification answers the question, what is in the image? So as you can see in the image, the model says cat. So that's it. It doesn't tell us where the cat is. It's just know that a cat is present. Next, we have classification plus localization. So on this one, we add localization. So now, not only does the model knows that there's a cat, it also shows where it is using a bounding box. So this is something called image localization. And here, things get more complex. The model detects multiple objects in a single image. So it identifies that there's a cat, there's a dog, and there's a duck. And it draws separate bounding boxes for each of them. This is classic object detection. Multiple objects, and each located and labeled. And what we have here in the next is the instance segmentation. So instead of just bounding boxes, we go on a step further. We outline each object by pixel. So each object, even if it belongs to the same class, it is treated as a separate instance. Example as this one. So in the image, both here we both cats are labeled um, individually and separate with a separate segment. Compared to the semantic here, the one is this one, no? The one treats all object of the same class as a single group. Notice how all the sheep are colored the same, no? With no distinction between individuals. So instance segmentation is a powerful technique, no? Because it gives us both the precision of segmentation and the separation of object instances. So to summarize this slide here, classification is what is it And detection is what is it plus where is it. And segmentation is what, where, and which exact pixels belong to each object. So these levels of understanding are key in everything from self-driving cars to medical imaging. And as we go deeper into each, so the complexity and precision both increases. Okay, now that we know what object detection does, locating and classifying objects using bounding boxes, so let's take a look at a very important question. How do we evaluate how good our object detector is? Okay, so in this example, um, the green box here represents the ground truth. This is the correct answer, usually labeled by a human expert. And the red box is the output proposed by our model. So this is the predicted bounding boxes or bounding box. Now the key question is how close is our prediction to the actual object? Or put another way, how well does the red box match the green one? So to assess that, we need a metric, and that's where the the intersection over union or IOU. So we have the inter intersection over union or IOU. So it is a ratio that tells us how much the predicted boxes or the predicted box overlaps with the ground truth box here. Okay, so if the box or if the red box is perfectly overlaps the green box, so the IOU is 1. If they don't overlap at all, so in case the square is here, so the IOU is 0 in this case, or somewhat 0. So IOU helps us decide whether detection is considered correct or not. So in most object detection tasks, a prediction is considered a true positive if the IOU is above a certain threshold. It is commonly the IOU is zero point 0.5 above zero point 0.5. So in practice, this is how we quantitatively evaluate object detection performance, not just visually, but with a measurable score. Okay, let me remove this one. Okay, so let's continue our evaluation of bounding boxes. This time, focusing on how much of the correct area is actually covered by our predicted bounding boxes. So in this image, the green box again represents the ground truth. The red box is our model's uh, predicted bounding box. And this shaded region shows the overlap between the two boxes. Now, just by looking at it, we might say, hey, the red box covers maybe 90% of the green box. Well, that seems pretty good. And sure, at a glance, it does look like the model is doing a decent job. But where here's the catch. Is that really a good metric to use? Only considering how much of the ground truth is covered can be misleading because it ignores what is outside the ground truth that the model may have wrongly included. Example here is the background here, no? Or the red box is clearly wider, as you can see here, than the green box. It extends beyond the actual object here, the car here, no? So that means it is including background pixels here, or even parts of other objects. So if we only ask how much of the ground truth is covered, we might give the model a false sense of high accuracy. To more fairly evaluate this, we use a metric called the IOU, or um, the intersection over union. So which compares the area of overlap against the total area covered by both boxes. So it gives us a much more balanced view of how accurate our prediction really is. We will explore IOU in more detail next, but just remember, coverage alone isn't enough. We need to measure both how much we got it right and how much extra we included. Okay? So let me remove this one. Mhm. Okay. Now let's talk about how we mathematically. Um, oh wait, this one. I'm so sorry. I clicked the previous one. Okay. And now let's talk about how we mathematically evaluate the quality of a predicted bounding box. And for that, we use a metric called the IOU. So in the image, we still have the green box as our ground truth and the red box as the predicted box. And the shaded area where they overlap, which is the intersection here. No? So you can see here in this part. So now let's take a look, no, at the formula. So IOU is the size of union over the size of prediction. So this means that we divide the area where both boxes overlap by the total area covered by both boxes combined. So this gives us a score between 0 and 1. So the score is a score of 1 means a perfect overlap. No? Our prediction was spot on, no, in this case. And a score of 0 means the boxes didn't overlap at all. So IOU is powerful because it penalizes both overestimation and underestimation. So even if our predicted box in this case includes the entire object but adds a lot of unnecessary background, so IOU here will drop. A commonly accepted threshold is, as we discussed in the previous slide, is zero point 0.5. So if the IOU is above zero point 0.5, we usually consider that a correct detection. But in high stakes application like medical imaging or autonomous driving, we might want a much higher IOU. To sum up, IOU considers both the size and alignment of the boxes. And higher IOU means better detection quality. And it's one of the standard metric used in evaluating object detection like YOLO, SSD, and faster RCNN. And we will just tackle those models later on. Now that we talk about how to assess individual bounding box predictions using IOU. So here we have another metric used to assess object detector performance, and it is called mean average precision or MAP. Okay, so now we've talked about how to access using the IOU. So let's take a look at how we evaluate and compare entire object detection models, and that's where MAP or mean average precision comes in. MAP is widely considered as the gold standard for comparing object detections or object detection models on the same dataset. Why? Because it combines multiple aspects of performance, like let me write this one. So it is aggregation of several matrix s- here, which is the um, what we have here is the precision, 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 and recall. So precision and recall is one of the metrics to be used for mean and average precision. And well, let's break it down, no, and what these metrics tells us. So precision, it tells us how many of the detected boxes are actually correct. And recall is it tells us how many of the actual objects we manage to detect. And MAP brings this together by calculating the area under the precision recall curve. No? If you plot this one, and then averaging the results across all classes. Well, we will just tackle it later, no, how it works on how to calculate this one. But MAP doesn't just tell us if a model got one box right. It gives us a more holistic view of how well a model performs across different classes and thresholds. Okay, let me remove this one. Okay. So what we have here is these are the two components or core components of MAP. So these are the precision and recall. So this is are essential for evaluating object detection models. So what we have here is we have the precision. Precision is or tell us when the model predicts something positive, like example detecting a dog. So how often it is actually correct. So we have TP or true positives means the model predicted correctly, and we have false positives means the model predicted something but it was wrong. So this is a very important um, parameters here for this in this metric precision. So precision focuses on how accurate the model's predictions are. So high precision means few false alarms. And what we have here is recall. So recall is um, recall answers out of all the actual positives in the image, how many did the model manage to detect? So here we have this new parameter here, false negatives. So false negatives means that the model missed something, so it should have detected, no, in this case. So if we try to draw this one, we like to draw something. So let's say we have um, circles here, and we have detected most of the circles, and we miss out some of it. No? So as you can see, we miss something, objects of circles here. So this means these are the false negatives. So recall measures how complete the model's detections are. So high recall means few are misses. So if we include this one here, so this means that it has high recall. So map or MAP, this one, if you combine these two by plotting precision and recall at different thresholds and calculating the area under the curve, so it then averages this overall object classes to get a single balanced performance score. In short, precision, um, precision, trust your detections, recall, don't miss detections, and MAP combines both to judge the overall detection quality. So this is why MAP is so important when comparing object detection models. Okay, anyway, this one. Okay. To fully understand how mean average precision or MAP is or how it works, so let's break down one of its components, which is the precision. So on this slide, our object detection model predicted three objects as a dog in this case. So the first and the third images are dogs, and the predictions are correct. So these are true positives. But in the middle, the model labeled a cat as a dog in this case. So that's a false positive. Since it incorrectly predicted the objects class, so now how do we calculate precision? So if you recall, precision is equal to true positives over true positives plus false positives. So if we calculate it, so we have, so let's say precision is equal to TP over TP plus false positives. So what we have here is we have two true positives here because it detects actually a dog here. So we have two over 2 positive, which is 2 plus 1 false positive because instead of cat, it detects or label it as a dog. So what we have here is we have 2/3. Or if we convert it into a floating number, it would be some I think it is 66.667, I suppose. Or let's say it is 67%. Okay? So what it tells us is that about 67% of the detections were correct in this case. So precision answers the question when the model said it found a dog, how often was it right? So this example highlights how precision penalizes false alarms. So even though the model found most dogs, it also made a mistake, and precision reflects that, no? And what else okay, I think we're really good here. Okay, next would be what what is next? Okay, about recall. So following up precision, so let's now take a look at the other key metric for MAP, which is recall. So recall answers the question of all actual objects in the image, how many did the model correctly detect? So in this slide, we have three actual dogs. So let me fasten this one. Okay. Okay, so in this slide, so we have three actual dogs in the image, and the model correctly predicted the first and the third as a dog. However, it missed the second one here. So this floppy white dog in the middle wasn't detected at all. So this means we have true positives and one false negative. A dog that the model missed. So to calculate recall, so we have recall. Recall is true positives over true positives plus false negative. So what we have here is we have true positive is um, 2 because we detected right two instances here, 2 plus 1 false negative. So we have still we have 2/3 in this case. Still, it has somewhat 67% recall. Okay, so okay, let me. So we have 67 here, right? So I just calculated here again if it is really 66.7 or 67%. Okay, so while precision tells us how accurate our model predictions are, so recall tells us how complete our detections are. So in other words, we find everything we were supposed to in this case. So if a model has a low recall, it might be too cautious and end up missing real objects. And this could be dangerous in some applications like security, healthcare, or autonomous driving. So if you have if a low recall in this case. So again, if you have high precision, well, detects well it detects most of the it detects most of the it identifies most object as a dog, no, for this example, if this in this case, if the model Okay, let me check my mouse again because it has. Okay, I have a problem with my mouse right now. Let me. Okay, let me check. Okay. Okay, again. So if I will go back, precision answers what we predicted. So how much was correct, and recall answers of what exists. How much did we find, no, in this case? So if you have a raw recall, so it might be too cautious and end up miss real objects like this one. If you have low recall here, example here, if you have another images of dogs here, let's say we have another image here, but we missed uh, detecting those dogs here. So it will raise a low score on recall. So if a model has low recall, so well, it is very dangerous. So if you want to build applications like in security, in healthcare, or autonomous driving, so well, it's quite dangerous if you have if your recall is too low. And what we have here again is the okay. Um, if if we have low precision also, we will misdiagnose. No example in medical imaging. So if we misdiagnose those lesions, example in brain, no? So in brain we misdiagnose this one as hemorrhagic. Let's say hemorrhagic. So and instead this one is what what ischemic in this case, no? So I misspelled this one. So this will raise a misdiagnosis. Instead, this one the model predicts this is hemorrhagic instead of ischemic. So in regards to precision, this one is very dangerous also. So we misdiagnose uh, a certain lesion here. So that's why it should be balanced. No, precision recall should be high in regards to this type of applications like in security, healthcare, and autonomous driving. Okay, so MAP considers both these measures over different thresholds to judge overall model quality. Okay, oops. Okay. Okay, so let's now talk about an important detail that can significantly influence both precision and recall, and ultimately the MAP score, and that's the IOU threshold. As we discussed before, an IOU helps us determine whether a predicted bounding box matches the ground truth. But how strict we are defining a match depends on IOU threshold we set. So in most cases, an IOU threshold of zero point 0.5 is considered acceptable, meaning the predicted boxes must overlap at least 50% with the ground truth to count as it is correct. But what happened when we change that threshold? So example here, no, let me write it up. Okay, so let's say if our model predict bounding boxes for all three dogs in this case, but maybe in the middle, okay, let me, oops, I think I didn't. Okay, all right. So okay, back to the slide. So maybe the middle image box isn't quietly aligned, for example, or it is quite it's a bit loose. So if we were using a strict IOU, a strict IOU example here is, so we have IOU threshold like 0.75 or 9 in this case. We might say this prediction is not good enough and reject and we will reject it as a false positive. So on the other hand, we are more lenient threshold, like let's say zero point 0.3 or zero point 0.4. So we might accept it in this case. So this decision has a direct impact with regards to adding IOU threshold. So a high threshold results in fewer true positives, so it is low recall. So in case if you set the threshold here as 0.75 or 9, so well it will raise to low recall. So a lower threshold, so we may accept more detections, but at the cost of possibly low precision. So in this case, no. So if IOU threshold is this one, no, less. So it may raise a lower precision here. So it is, well, guys, no, it is depending on the task whether it requires high accuracy or broad detection coverage. So we might tweak this threshold. So that's why when comparing object detection or object detection models, you may see there is MAP at zero point 0.5, there is MAP at 0.75, or we have MAP from zero point 0.5 to 0.95. If you check those papers with determining the performance of object detection, so we will encounter this one. So it says that NAP at zero point 0.5, so it uses IO threshold zero point 0.5, and for 0.75 it use IOU 0.75, and the last is 0.95. So to get the picture of a fuller picture of the performance of a model. So as you can see in the next slide, so I have problems here with my mouse again. So let me, okay, oops. Okay, so now we bring everything together with the full picture of precision, mean average precision or MAP. And we've seen earlier, we evaluate a model's performance using precision and recall. But how do we turn those into a single score? So then, uh, that's where average precision AP here, no? As you can see, um, for a given class like example dog or a cat or a car, so we can plot a precision recall curve, as you can see here, no? By adjusting the confidence of the IOU. So the area under this curve, example, what we have here, gives us an average precision AP for the specific class. So with this formula no, here, so this one is the average precision of class K, and we have the N here, number of classes, and we have the formula for mean average here. So if you're working with 10 classes or 10 object classes, so you calculate the AP of each one, then average them to get the final MAP score. On the right side on the slide, no, we can see an example of precision recall curves for multiple classes like example bowl, coffee mug, soda can, and the others, no, all. And this one is the combined, no? Can this one all combined curve. So this gives us a powerful single metric that tells us how accurate a model is for precision, how accurate the detections are in recall. So and how consistently it performs across different object types. So in practice, the higher the MAP, the better the model performs across the board. No? And what we have here in the next slide is to benchmark those it is a benchmark data set for checking out if your detection if your model gives us a high MAP, no, in this case. So as we wrap up our understanding of object detection and evaluation metrics like MAP, it is important to also talk about where we get the data to train and evaluate these models. So one of the most widely used datasets is the COCO dataset, which is a standard for common objects in context. So, well, if you try to create your own object detection models, so this one is a right dataset for you to check your design models if it has a high MAP in this case. So COCO is a large-scale benchmark dataset developed for object detection, segmentation, and image captioning tasks. So, well, it is incredibly valuable because it has more than 300. I think that is 300. Let me write it down. It has, I think, oops, that there are 330K images, and this one is images, and I think there are 200K labeled classes. So I know 200K labeled in this 300K images, and we have okay. I think this one. Let me remove this one. Okay. Okay. Okay, so as you can see, we have 330K image. So there is this one. We have greater to 200K labeled and over 1.5 million objects are noted for object instances. We have 80 object categories and other 91 categories also another one, no? Another 91. So I think this one are the skies, grass, road, which what is in the background of some of the image they added it. So they have pixel annotations for object detections and so on. So all of this, which annotations make Coco one of the most challenging and realistic data sets because it doesn't just focus on isolated objects. So it puts them in real world contexts, often with occlusions, crowding, and background clutter. So you can see on this no this image. This is an example of images from Coco dataset where objects like people, animals, and vehicles are annotated with pixel level. In this case, pixel level segmentation mask. So in terms of evaluation, Coco is also the standard dataset used in major competitions like those for YOLO, mass RCNN, and other sort of models, making it the go-to benchmark for comparing detection performance using metrics like MAP. So let's say the MAP is for MAP at this range, no, for IOU threshold 95. So if you want to build or test an object detection model, so you can use Coco. Coco is the one for the best places to start. And let me again, let me. I do have a problem with my mouse right now. Okay, okay, okay. So what we have here, okay. To wrap up our discussion on the Coco dataset, let's take a look at how it used to benchmark and compare object detection models over time. So this graph shows the leaderboards or the leaderboard performance on the Coco test dev or the data set, no? Specifically with the box for MAP, no? Box MAP. So the same one we've been learning out, no? About recently. So each point of this chart represents a model performance. And this line here um, connects the models that achieve the highest box MAP. At this time, we have this, what this one? I think this EVA, the model EVA. So these are the state of the art, no, or SOTA models in object detection. So if we check this one, no, around somewhat 2015, faster RCNN and faster RCNN laid the foundation. So then we have the SSD 512 and Retenanet in this case, which improved performance while speeding up inference in 2017. And we have what else? We have mass RCNN here and Cascade mass RCNN. This one Cascade, no, this push accuracy in this case further by combining detection with segmentation. This one mass RCNN is for segmentation. More recently, advanced models like we have Swin L and what we have here, FocalNet and Eva have broken it into what we have a 60 maybe here. So thanks for that. It uses transformers and for large scale training. No? So this leaderboard helps researchers and developers to see what techniques are working, choose a model depending on the trade-off between speed and accuracy, and most importantly, benchmark their own models fairly using a consistent data set and metric. So if you are interested in checking out in real time, the link here, no, the link at the in this one, no, papers with code, brings you to where this chart is updated live as a new models are published. Now that we understand how object detection models predict bounding boxes, so there's one final and very important step in refining those predictions. This non-maximum suppression or NMS. So when an object detection analyzes an image, it often predicts multiple overlapping, as you can see here. So there is a multiple overlapping boxes. So for the same object like this one, no, specifically if there's a high confidence, it mo- it if it has a high confidence, so it will detects multiple nearby regions. Um, as you can see in this example, before applying NMS, so we have several yellow boxes here all around on the same car. So obviously, we don't want to report five detections for one object. So we need a way to clean this up. So that's what a non-max suppression or non-maximum suppression does. So it will start with all overlapping bounding boxes, then take a look the confidence scores. So how confident the model is that the object is a car, then it will pick up the box of the highest confidence or score and move it to the final list, and then compare this box with the remaining ones with calculating the IOU or the intersection over union. And then if any other box overlaps or exceeds the set or typically the IOU threshold zero point 0.5, so we consider it redundant and suppress it, or we will need to discard it or reject it. And next is we repeat the process for all boxes. And then after that, this one will be the final box, no? In this case, or the final prediction. So this one is the best fitting box per the number of object detections here. So this will reduce false positives, cleans up duplicate detections, and help us it will help us or helps your final predictions look clean and accurate. So while your model might initially be generous in proposing boxes, so non-maximum suppression will help it make a final decision on what to keep. Because as you can see here, in reality, there will be a lot of detection in just one object here. So they were representatives or representations. So that's why we need to, what will be the best box here that represents this object? So it should be, you will use the non-maximum suppression here. Then if you follow these steps, then using the IOU threshold, then it will represent this one.